Right. Let me say there's I don't want you to memorize this table, but there are two things that you do need to memorize about this table. One is fluorine. What's special about fluorine? Fluorine we call the most powerful oxidizer on the chart. It might not be the most powerful oxidizer in the universe, but it's the most powerful on the chart. Just like, what was the strongest acid on that chart? The acid-base chart. HClO4, which is called perchloric acid. Perchloric was the strongest, but there are stronger acids than perchloric, they just aren't on that chart. There are stronger oxides than fluorine, it's just not on this chart, but fluorine is the strongest on this chart, so you should memorize that. The conjugate is fluoride. And fluoride's what we call a reducer. Fluoride has electrons, but does fluoride want to give up the electrons? Because reducers give up electrons. Oxidizers take electrons. So does fluoride want to give up its electron? Once it has it? No. Once fluorine gains that electron, it's pretty much stuck on there. So what we say is fluorine is the most powerful oxidizer. The absolute worst reducer on the chart is fluoride. Well, fluoride doesn't want to give up electrons, but sodium does. Give up electrons quite easily. In fact, sodium gave up electrons to water in the video. But lithium is at the top. Lithium is what we call the most powerful reducer. And so this is the one that's easiest to take electrons from, lithium. If you're going to take electrons, take it from lithium. That means its conjugate, lithium ion. Is lithium ion a good oxidizer? Does it really want electrons? No. And so lithium metal is the most powerful reducer. Its conjugate, lithium ion, is the absolute weakest oxidizer on the chart. So the conjugate relationship is oxidizer-reducer. Now it depends. If you look at older charts, they flip it. The older charts have the reducers on the left and the oxidizers on the right. And so the older charts have lithium at the top left and then work their way down. And since we don't know if we're using an older chart or a newer chart, we just memorize lithium and fluorine. If we memorize lithium metal and fluorine elemental, not fluoride, then we always know the orientation, because fluorine is the most powerful oxidizer, lithium is the most powerful reducer, and the rest should follow from there. Table is like our normal orientation. Fluorine, the strongest oxidizer, and lithium, the strongest reducer. Our normal orientation. Same thing with this chart. This chart's the same. But there are other charts that look a little different. And, let me just show you what they look like. Take a look at this chart here. Some people prefer this chart versus the other chart. But what do you notice that's different? On our chart, at the top left was F2, fluorine. On this chart, the top left is lithium. But you know, there's no right side up, there's no upside down. You know, it doesn't matter what orientation it is. You should know that this one, lithium, is the most powerful, not a reducer, the most powerful reducer on the chart. So everything else. That means lithium ion is the absolute worst oxidizer. And so down here is the best oxidizer on the chart. Down here would be fluorine. And so it doesn't matter if you're reading it upside down or right side up. There is no upside down or right side up. It just depends on how you want to write the table. Be aware of that. A lot of people, they have a way of memorizing. The way they memorize it, top left is strongest oxidizer. But if I gave this chart and they said top left is strongest oxidizer, they'd be wrong. They'd be right here. Top left is the strongest oxidizer. No problem with that. All right, so this gives us some ideas, you know, of behavior. You know, metals are electron rich, as you'd expect. These are electron poor species. They're electron poor in different ways. Maybe they have a high positive charge, or maybe they just want an electron. Like fluorine doesn't have a high positive charge, it just wants an electron. That's it. And so this way we can understand more about the properties of different compounds. And so typically the way we analyze things is like this. So let's talk about there are two ways that I could analyze something, like HCl, for example. HCl is a very common chemical. What would you call HCl? If I didn't write gas or AQ, what would you call HCl? Hydrochloric acid. So if we look at hydrochloric acid, you know, and I asked you what are the chemical properties? What would you say? Acidic. Yeah, it's an acid. Hydrochloric acid, it's an acid. And so, it's an acid. What do acids do? Acids donate protons to bases. And so, it's an acid that reacts with bases. What are the bases? The bases are those things on the left of the chart. And so, these are the bases here. And so hydrochloric acid will react with all these species on the right-hand side of this chart, all of them. Obviously, water, hydroxide to form water. And so it's an acid, reacts with bases. Is that it? No, that's not it. It also undergoes metathesis reactions. Metathesis, what did I call metathesis? I called it favorable ion combinations. Favorable ion combinations would be like H+. What ions does H+ like? H+ likes bases, such as like carbonate, phosphate, hydroxide, etc. Likes bases. You can see the bases there, cyanide. Well, that's just an acid-base reaction. You know, acids have the cation H+. What about chloride? Does chloride like anything? Yeah, chloride does. What does chloride like? Sodium. It doesn't really like sodium. It's the only way to get sodium and chloride together is to force them together. How you force them together, let's say you had salt water. When do the sodium and chlorides come together to form a crystal salt? When you evaporate all the water. What happens is the pool gets smaller and smaller, and eventually the ions are going to be forced together, and once all that water evaporates, then you're left with salt residue. We want things that come together immediately upon contact. What things come together immediately upon contact with chloride are silver ions, mercury 1 ions, and what else? Potassium. Not potassium. See, I know it's going to be no reaction. It's going to be no reaction with potassium. It's going to be no reaction with sodium. It's going to be no reaction with iron 3. It's going to be no reaction with, name an ion. Lithium, no reaction. I know that because I don't want to test every single one. I just memorize this little patterns like this. You get it?
Well, no, mine doesn't say this. Lithium is +1, chlorine is -1. Wouldn't that be?
Yeah, you would expect it to come together, but they're only forced. There's a difference between this. They come together due to evaporation. Let me show you ions that come together naturally. Maybe on a video, just show you. This is what it looks like when the ions really like each other. And so, see, immediately when either the, well actually this is silver ions and chloride ions coming together. This white cloudy stuff is silver chloride. It's precipitate. And so immediately when the silver ions and the chloride ions come together, they coalesce into a solid. It's called precipitation. Whereas if you had sodium ions and chloride ions, would they immediately coalesce into white crystals of sodium chloride? No. So this is a difference. The difference is immediately when you add the silver to the chloride, you get this come together. Lithium and eventually lithium and chloride will come together, but you have to remove all the water, and then they'll come together. As long as there's water present, they're going to stay away from each other. They're going to stay away from each other until the very bitter end. Precipitation. This is thiosulfate. It goes to silver sulfide and changes. This is barium sulfate. These are all precipitates. This is all in water. It's hard to tell. Let me show you where they actually showed the drops come in. This is lead likes iodide. Remember that? Let's see this one. So they're suspending a drop. There's a drop above the liquid there. You see immediately when the lead hits the iodide, the lead and iodide come together to form that cloudy white, cloudy yellow precipitate. We could have predicted that one because we know that lead and iodide like each other. How do we know? Because we've memorized our rules. And so if I add HCl to a solution that contains silver ions, they're going to come together, mercury 1 ions and lead. Well, what if I had an iron 3? If I had a solution containing iron 3, will HCl react with it? No, it doesn't. And so this is how we figure it out. I mean, we will figure it out. Okay, that's metathesis. And then we have redox, which comes next. When we have redox, we know that HCl consists of H plus and Cl minus. H plus is what we call an oxidizing agent, or an OA. Cl minus is a reducing agent, here, or Ra. Cl minus is a very poor reducing agent, and so it's not very reactive. But H plus is a moderate oxidizing agent. And you don't have to have that memorized. You just look it up on the chart here. I'll just show you. The absolute worst reducing agent on the chart is fluoride, but chloride is not that far behind. You see chloride's here. So chloride is kind of unreactive, like fluoride's unreactive in a redox reaction. Chloride's reactive in metathesis. Fluoride loves calcium ions. But anyway, here's chloride. These are all unreactive. Here's water. How reactive is water? Very unreactive. Then we go on. But H plus occurs on the other side. So fluorine here, we work our way down. H plus here. Now this chart has a very useful feature to it. If I reacted H plus with H2, do you expect anything to happen? If you take H plus and H2, there's a tug of war for electrons. But each side consists of hydrogen. And no side has an advantage. And so when we think about H plus reacting with H2, H plus wants electrons, H2 can give them up. We think no reaction. However, if something gives up electrons easier than H2, maybe H plus will be successful. And so what gives up electrons easier? Well, anything towards lithium gives up electrons easier. And so lead gives up electrons easier. And so the interesting feature about this table is this. We can rapidly see what H plus will react with. Will H plus react with lead? Yes. It reacts with lead metal. So acid, will it eat up lead? Acid, will it eat up tin metal? Yes. Iron? Yes. Zinc? Yes. Aluminum? Yes. However, will acid eat up copper? No, because copper is more difficult. That is, copper is not as good of a reducing agent as these. And so the way we can easily see this is by this. However, there are some acids in here that aren't so clear. For example, sulfate and H plus. What acid does sulfate and H plus make? If I have H plus and sulfate, it makes sulfuric acid. Sulfuric acid is capable of reacting anything down here. If I wanted to react copper metal, I need something more powerful than copper ion. So what's more powerful than copper ion? Anything towards fluorine. And so if I really wanted to react with copper metal, I probably should use iodine, oxygen, iron 3, silver ion, or nitrate and H plus. What's nitrate and H plus make? HNO3. HNO3 is called nitric acid. So if I want to dissolve copper metal, I got to use nitric acid. I cannot use hydrochloric acid. Like that. And so these things we'll see as we go along. You know, you don't have to get it all. Like I said, it doesn't all come like in one click. And so what we're going to do now is let's get a little bit of practice. I just want to see your understanding of oxidation states. We'll get a little practice doing oxidation states here. kind of hard to see. There's also practice in your supplement. There's a whole bunch of oxidation state problems in the supplement. Chem compact B and Chem compact G in the supplement are chemical reactions. The Chem compact B and Chem compact G, I talked about how many pages, it's like 50 pages worth of the next reading, but they presented differently from what I just did, so it's helpful, but not as helpful as you might wish for. Well, let's try to assign oxidation states to the underlying element. This is typical multiple choice. They ask for one element. I asked for both. And so here they only interested in aluminum, but I'd ask what is the oxidation state of aluminum and oxygen. There, not just the aluminum. But since it's multiple choice, well, I guess you could do a multiple choice one. But anyway, so some of these we already did. Figure it out again. So we have P4, Al2O3, MnO4 minus, NaH, and H2O2.
We're doing if you're not there.
I'm sorry?
On these new cards, you want us to do?
Yeah. Okay, go ahead. Just tell me the charge on the underlying element. You could do both also. Al2O3, MnO4 minus, NaH, H2O2, and Fe3O4. Now, a lot of people think that's it, the ultimate aim, the ultimate goal is to be able to figure out these numbers. But, if you think about it, anybody can figure out these numbers. It's just a set of rules. You just follow the set of rules. And so figuring out the number is no big deal. You know what the big deal is? The big deal is interpreting the numbers. Can you interpret the numbers? Because a +3 for one species is not the same as a +3 for another species. And the same thing goes with minus charges. And so if you're just calculating the numbers, a computer program can do that. You don't need a real human to do that. But in analyzing the numbers, you need a real human to do that, because a computer program might have a hard time. Because there are many. Well, maybe not a hard time, but and so this is why you need to memorize some of the properties that are associated with some of these things.